Oh, no, that's okay.
Well, I'll just move it over a little
Okay,
bit. So
that's
okay, you got your space?
Yep.
Great.
Okay, thanks.
Professor Johnson?
Yeah.
I got a new piece of chocolate you needed.
Oh, great. Yeah, I'm down to the nub, all right. Appreciate it. I'm not going to put it there. I'll forget it. Thanks.
Can we tilt it this way? This one's here. Oh, no, no, that way. Push it back down. Oh, no.
Okay, so here's where we're at. We're going to try and do a
You can get the
calculation that gets us started on things. And so it's a one-stage equilibrium separation. The feed is set. There are 2 degrees of freedom. These kind of problems divide themselves into problems where Q may be of little interest. And problems where Q is important. So we'll talk about these first. When Q is of no interest, then neither are the enthalpies. Neither HF nor H nor H are interesting. So there may be a Q. There's a product here, there's a product here. This is the overhead product, this is the bottoms product. We would like to set our 2 degrees of freedom and learn how to calculate everything else. So the idea is set your 2 degrees of freedom. And find everybody else. Now, we're going to do this in the special case where, let's see, we defined K values at one point, so the definition of a Ki is Yi divided by Xi. And this is the definition. And we'll do this for, I guess, ideal case. The ideal case, and C equal to 3. So a good ideal case when C is equal to 3 is 1 equals butane, 2 equals pentane, 3 equals hexane. I wouldn't necessarily have to specialize this. I can actually, by whatever we're going to talk about, do as many components as you want. Our equilibrium is, says F equals C minus P plus 2, so it's C. And the equilibrium variables are the 2 times C minus 1 mole fractions plus the temperature and pressure, which is 2C, so that's the number of variables. F is C, so the number of equilibrium equations is 2C minus C, which is C. So in this case, here's what our C equations look like. Yi equals Ki of T and P times Xi. And the Ki of T's and P's are given. Ki of T and P are given, and they're given like this. you set a P, then you are handed curves for your components. Here they might be like this. Plot K up this way, plot T over this way, and I'll only ever be interested in T's in the range where these guys are not all greater than 1 or not all less than 1. So there'll be a T star here, and there'll be a T star here, and over here, they're all less than 1. And over here, they're all greater than 1. And I'll never be able to get solutions to the problems when all the k's are either greater than 1 or all the k's are less than 1. So I'll be interested in some range T star, T down star, T up star. T down star and T up star will give me a range. And this range will depend upon P. So if I change P, I'll change that range. Now there's something kind of nice about these systems. And what's nice about them is that K, I, T, and P depends, times P depends only on T. So if you have this diagram at some P of interest where you went and measured it, you can get it at any other P by recognizing that Ki, T, and P times P, it depends only on T. So it'd probably be a smart idea that every time you come across a Ki, you might write it as Ki of T and P times P divided by P. The numerator then depends only on T, and the denominator depends only on P. We'll take advantage of that when it suits us to take advantage of that, and otherwise we'll, that's a useful thing, yeah.
What if you have gas, would K depend on P? What if you have gas, would K depend on P heavily more?
You're missing a point here. I've got gas and liquid. I mean, I'm taking a feed here without telling you much about it. And we're going to control this Q and get an overhead product and a bottom product. But this is vapor, and this is liquid. So the number of phases P equals 2. There's one of them, there's the other one. These are assumed to be in equilibrium. I don't care whether you've got a liquid feed coming in which case I'll put positive Q in. I don't care if you've got a vapor feed coming in which case I'll take Q out. But I'll create 2 phases. I'll create 2 phases for the clear reason that that's the only way I can get an equilibrium, and that's the only way I can get a separation. So this is where we stand, and I think last time we talked about bubble point and dew point. So let me just remind you of what the bubble point and dew point equations look like. So if somebody gives you a pressure and a composition, so if you've got a pressure and a composition, you can define T bubble point and T dew point. Now, you can always do this, but for these systems, it goes like this. The summation of Ki of T and P. How the hell does it go? Minus 1 times the Zi's are equal to 0. The solution to this at the given P's and Zi's, solution to this is called T bubble point. If you rearrange the calculation slightly differently and do this, 1 by Ki of T and P minus 1 times the Zi's, set it equal to 0, you will get something called T dew point. Now, Z's are the compositions you're interested in. It doesn't say anything about whether these Z's are liquids or vapors. But if I'm doing a bubble point, these Z's will be X's, and this temperature will be the temperature at which the first bubble appears. If I'm doing a dew point, these Z's will be Y's, and this temperature will be the temperature at which the first drop of liquid appears, all right? So they're interesting variables, and we noticed that, I guess we noticed the T bubble point is less than T dew point, is less than T up star, is greater than T down star. So those are the facts we've derived so far about the bubble point calculation. Now we're going to go try and solve a separation problem. And we want more than just a bubble of vapor or a drop of liquid. So we'll write down our problem. Now, the first case is that I don't care about Q. So what have I got? I've got the C equilibrium equations. I've got C material balances for a grand total of 2C.
Question.
So I've got 2C equations, and of course, if I count them up, I'll have 2C plus 2 variables. And that means the number of variables is 2 above the number of equations, so I set 2 variables, and I go and try and solve. Yeah?
What's the physical meaning of Z? What is
Z is, well, the physical meaning of Z is always, in our problems, it's the feed composition. Okay? Now, I don't care whether the feed is a liquid or a vapor or anything. Z is the feed composition. I'm going to be very interested in the bubble point temperature and the dew point temperature for the feed composition, because my temperature in my system must lie. So I'm going to observe that I cannot get a solution to my, I haven't even written the problem yet, but this must be greater than the bubble point of the feed and less than the dew point of the feed. Now, whether or not the feed is vapor or liquid, I don't care. Its composition is Zi. This equation gives you the bubble point at the pressure P. This equation gives you the dew point at the pressure P. You change the pressure, gets a new bubble point, a new dew point, gives a new range of temperature for the solution to the problem. But my solution, yeah, we can sketch this. You can see this in a picture if I had C equal to 2. If I have C equal to 2, I might have a picture that looks like this. And I've got a composition here, Z. I start, this is liquid here, this is vapor up here. If I start heating this up, that's the bubble point temperature. If I continue to heat it, that's the dew point temperature. I continue to heat it up here in the vapor range. All at the composition Z. Up here, I'd call the ZY. Down here, I'd call the ZX. However, if I'm going to get a separation, I need to be in here. So I get compositions in equilibrium, one of which is greater than Z and one of which is less than Z. So I'm expecting, well, too bad I erased the picture, but you can sort of see it outlined here. When I get these compositions up here and these compositions down here, they're going to bear a certain relationship to Z. We'll see how this goes. So that's where we stand. Now, so what we probably have to do is write our equations down and decide how we want to go about this. So, yeah.
Is there 2 phases on that line? Or
One phase.
what
two
about
phases.
in that line? Where they
This
meet?
is 2 phases in here.
What about the line though? Which one?
What about what line?
Right here.
That is saturated vapor. This is saturated liquid.
So
That means there's a vapor in equilibrium with it that has a composition right there. And this means there's a liquid that has a composition right here. But this is the one bubble of vapor coming off when I hit bubble point. Look,
so 2 phases?
look, look, look. I've been informed of a lot of things. I'll get to you. I won't forget. I've been told you guys have been doing bubble point and dew point calculations like nobody's business in your first thermo and in your material balance course. I know that to be true, so don't tell me no. I've been told by the people that teach those courses that that is true. So I'm not going to beat to death bubble point and dew points. I'm just going to tell you what they look like and what a picture looks like. And I am not going to reteach you any stuff that you should know coming in here. We'll never get anywhere if we do that. So you go out and read, you go out and check, you go out and ask somebody. We ain't going to do it here. Shoot.
Just to clarify, K is the reaction, is the equilibrium constant for
Well,
evaporation?
if you want to look at it that way, yeah. Okay. K is simply a definition. If you know the value of K, let's suppose you got a K greater than 1. This means that this component has a higher composition in the vapor than it does in the liquid. Suppose you got a K less than 1. This means this composition has a lower composition in the vapor than it does in the liquid. That's what these Ks mean, but they're just definitions. I need data to proceed. All right? Clear? No? So you guys are
Third year.
experts on this shit, right? We are assuming, rightly or wrongly, I don't care about the truth. You guys are experts on this. Okay, so let's write down some equations and begin to try and do something. But this picture at C equal to 2 basically explains everything. Okay, my equations. Well, I got C equilibrium equations. I equal 1 to C. I must have data for this. This is where the data comes in. Now I got material balance equations that go something like this. How shall I do this? ZIF equals XIL plus YIV. I got C of these. So as long as I'm not interested in heat, I've got C linear equations here, and they would be beautiful because this is almost linear. The trouble is that these curves are not straight lines. So T and P come in here, but the P part is easy because I'll probably write P here and P here, XI here, I could. Here, KI of T and P times P depends only on T. I got a P down here, which is straightforward. So let's have a look at our equation. Now, the thing we want to do, let me tell you what the aim is here. I could have lots of 2C equations, even with just 3 components. I've got 6 equations. So, what would be my unknowns in this case? I would say my 6 equations for C equal to 3. I would say my unknowns are Y1, Y2, X1, X2, L, and V. Those would be the things I would like to calculate. Gonna have to set 2 things up in order to go about this. So here's our first aim. Our first aim is to reduce our problem to 1 equation and 1 variable.